Beneath the gentle slopes of the Jura Mountains and the plains surrounding Geneva, a scientific instrument of staggering complexity circles through bedrock and clay. The Large Hadron Collider represents humanity's most ambitious attempt to recreate the conditions that existed mere fractions of a second after the Big Bang. Within its 27-kilometer circumference, protons accelerate to velocities approaching the speed of light before colliding with energies that dwarf anything naturally occurring on Earth today. These collisions tear open windows into realms of physics that remain otherwise inaccessible, allowing researchers to probe questions that have captivated minds for generations. The journey that brought CERN to construct such an extraordinary machine began decades earlier. Rooted in the progressive understanding that matter itself consists of smaller and smaller constituents, from molecules to atoms, atoms to nuclei and electrons, nuclei to protons and neutrons, and finally to the quarks and gluons that comprise those nuclear particles, each layer of discovery revealed new mysteries waiting beneath. The standard model of particle physics emerged as the culmination of countless experiments and theoretical breakthroughs, describing with remarkable precision how fundamental particles interact through 3 of the 4 known forces. Yet even as this framework proved itself through prediction after prediction, physicists recognized its incompleteness. The model offered no explanation for gravity at quantum scales, no candidate for the dark matter that apparently comprises most of the universe's mass, no insight into why antimatter vanished after the Big Bang while ordinary matter persisted. Constructing the Large Hadron Collider demanded innovations across numerous technological frontiers. The machine's superconducting magnets operate at temperatures colder than deep space, chilled to just 1.9 degrees above absolute zero using liquid helium. At such extreme cold, electrical resistance vanishes entirely, allowing currents to flow indefinitely through niobium-titanium cables. These currents generate magnetic fields powerful enough to bend the trajectories of particles moving at relativistic speeds, keeping them confined within their circular path despite carrying enormous kinetic energy. More than 1,600 superconducting dipole magnets line the tunnel, each weighing several tons and manufactured to exacting specifications. The engineering challenges were immense, requiring new techniques for fabricating, testing, and integrating components on scales never before attempted. When proton beams circulate through the accelerator, they don't travel as continuous streams, but rather as discrete bunches, each containing billions of particles compressed into spaces smaller than a human hair's width. Radio frequency cavities boost the energy of passing bunches with precisely timed electromagnetic fields, gradually accelerating particles through multiple passes until they reach their target energy. The beams travel in opposite directions through separate beam pipes, held in ultra-high vacuum to prevent collisions with stray gas molecules that would scatter particles out of the beam. At 4 points around the ring, the beams cross, and within those intersection regions, the carefully choreographed collisions occur. The detectors surrounding these collision points rank among the most sophisticated instruments ever built. Atlas and CMS, the 2 general-purpose detectors, each weigh thousands of tons and contain millions of individual sensing elements arranged in concentric layers. When particles emerge from a collision, they pass through multiple detection systems, each designed to measure different properties. Innermost tracking detectors record the curved paths of charged particles as they bend in magnetic fields, allowing physicists to determine their momentum. Calorimeters beyond the tracking layers absorb particles and measure their energy by recording the cascade of secondary particles they produce. Muon detectors form the outermost layer, identifying these penetrating particles that pass through the inner detectors largely unaffected. The entire apparatus must capture the debris from collisions occurring millions of times per second, filtering through vast quantities of data to identify potentially interesting events while discarding the mundane. The computing challenge alone stretches the boundaries of what's possible. Each collision produces far more data than can be stored, forcing sophisticated trigger systems to make split-second decisions about which events merit recording. Even after this filtering, the LHC experiments generate petabytes of data annually, distributed across a worldwide network of computing centers for analysis. Thousands of physicists at hundreds of institutions examine this data, writing algorithms to reconstruct what happened in each collision, searching for patterns that might indicate new particles or unexpected phenomena. And the Higgs boson search exemplified both the capabilities of the LHC and the careful, methodical approach required to claim discovery of a new particle. Theoretical predictions suggested that the Higgs field permeates all of space, and through interactions with this field, fundamental particles acquire mass. Without such a mechanism, the Standard Model falls apart, unable to explain why particles have the masses they do. Yet decades of searches at previous accelerators had failed to find direct evidence of the Higgs boson, the particle associated with this field. The LHC was designed with sufficient energy to produce Higgs bosons if they existed within the predicted mass range, but finding them among the billions of collision events required extraordinary precision and patience. The Higgs boson doesn't appear directly in detectors. Instead, it decays almost immediately into other particles, and physicists must infer its brief existence by examining the properties of these decay products. Multiple decay channels exist, each with different probabilities and different experimental challenges. A Higgs might decay into a pair of photons, or into 4 leptons via intermediate particles, or into W or Z bosons. Each channel produces a distinct signature in the detectors, but each also has backgrounds from other processes that can mimic the signal. Separating genuine Higgs events from these backgrounds demanded careful statistical analysis and comparison between the predictions of the Standard Model with and without the Higgs. As data accumulated during 2011 and 2012, both ATLAS and CMS saw hints emerging from the noise. Analyzing collision events where 2 photons appeared, researchers noticed a small excess at a particular mass around 125 billion electron volts. The 4-lepton channel showed a similar excess at the same mass. Individually, these hints might have been statistical fluctuations, but their alignment across different decay channels and different detectors grew increasingly difficult to explain as mere coincidence. The teams worked independently, each unaware of the other's detailed results until the final stages, ensuring that any discovery would be independently verified. The announcement in July 2012 that both experiments had observed a new particle consistent with the Higgs boson represented a triumph not just for CERN, but for the entire framework of theoretical physics that had predicted its existence. Further analysis confirmed that this particle behaved as expected, with the right spin, parity, and coupling strengths to other particles. Its discovery completed the particle content of the Standard Model, confirming that the mechanism by which particles acquire mass operates as theorized. The achievement earned François Englert and Peter Higgs the Nobel Prize in Physics the following year, they recognizing work they had published nearly 50 years earlier. Yet even as celebrations continued, physicists recognized that finding the Higgs opened as many questions as it answered. The measured mass of 125 giga-electron volts fell into a range that theoretical calculations suggested might be unstable, implying that the universe as we know it could be in a metastable state, potentially decaying to a lower energy configuration on timescales, far exceeding the current age of the universe. Moreover, the Higgs discovery, while confirming the Standard Model's predictions, didn't point toward the new physics that must exist beyond it. The model still lacked explanations for dark matter, dark energy, the matter-antimatter asymmetry, neutrino masses, and the apparent fine-tuning of fundamental constants. The quest to understand antimatter drives much of the research at CERN beyond the LHC's high-energy collisions. According to our best theories, the Big Bang should have produced equal amounts of matter and antimatter, particles identical to their ordinary counterparts except for opposite charge. When matter and antimatter meet, they annihilate in bursts of pure energy. If the early universe contained equal amounts, everything should have annihilated, leaving only radiation. Yet clearly, matter won out. Somehow, a tiny asymmetry favored matter over antimatter, allowing the 1 part in a billion excess to survive and form everything we see today. The anti-proton decelerator at CERN produces antimatter particles and slows them enough that they can be captured and studied with extraordinary precision. Experiments like ALPHA and ATRAP create antihydrogen by combining antiprotons with positrons, then trap these antiatoms using magnetic fields. By comparing the properties of antihydrogen with ordinary hydrogen, researchers can test whether antimatter obeys the same physical laws as matter. The CPT theorem, a cornerstone of quantum field theory, predicts perfect symmetry between matter and antimatter, meaning any difference in their behavior would shake physics to its foundations. So far, measurements show that antihydrogen's spectral lines match those of hydrogen with exquisite precision, and antimatter falls downward in Earth's gravity just as matter does, though experiments continue pushing these tests to ever greater accuracy. Other experiments at CERN examine how antimatter particles decay, searching for subtle asymmetries that might explain the universe's matter dominance. The LHCb experiment specializes in studying particles containing bottom quarks, which can oscillate between matter and antimatter states. By measuring how often these particles decay in particular ways versus their antimatter counterparts, physicists can quantify violations of CP symmetry, a combination of charge conjugation and parity. The Standard Model predicts some CP violation, and experiments have confirmed these predictions, but the amount predicted falls far short of what would be needed to explain the cosmic matter-antimatter imbalance. Either the Standard Model's CP violation mechanisms are incomplete, or entirely new physics operates at energy scales beyond current reach. Quarks, the constituents of protons and neutrons, never appear in isolation. The strong force that binds them together grows stronger as they separate, like a rubber band being stretched. Pull quarks far enough apart, and the energy invested becomes sufficient to create new quark-antiquark pairs. So instead of liberating individual quarks, you simply produce more bound particles. This property, called confinement, means quarks exist only within composite particles called hadrons. The most familiar hadrons are protons and neutrons, each containing 3 quarks, but countless other combinations are possible. Mesons contain a quark and an antiquark, while more exotic arrangements remained largely theoretical until recently. The LHC has enabled the discovery of numerous exotic hadrons that don't fit into simple categories. Tetraquarks, containing 4 quarks, pentaquarks, containing 5. 4 and other unusual configurations have been identified by examining the debris from high-energy collisions. These discoveries weren't entirely unexpected, since quantum chromodynamics, the theory describing the strong force, permits such states, but their properties help refine our understanding of how quarks interact and bind together. Some exotic hadrons appear as narrow resonances in mass spectra, indicating that they're relatively stable quantum states rather than merely transient fluctuations. Others show unexpected patterns in their decay products, suggesting structures more complex than simple quark clusters. The precision measurements at CERN extend beyond discovering new particles to examining known particles with unprecedented accuracy. The mass of the W boson, which mediates weak nuclear interactions, so it can be measured by reconstructing the kinematics of its decay products. Recent measurements have sparked considerable interest because they suggest a slight tension with Standard Model predictions, though the statistical significance remains under debate and requires further data to confirm. Similarly, measurements of how the Higgs boson couples to different particles test whether its interactions match theoretical expectations. Any deviation, even a small one, could point toward new particles or forces not included in the current theoretical framework. Dark matter remains one of the most profound mysteries in modern physics. Astronomical observations, from galactic rotation curves to gravitational lensing to the cosmic microwave background, all indicate that approximately 85% of the universe's matter doesn't emit, absorb, or reflect light. This dark matter makes its presence known only through gravitational effects, yet without it, galaxies would fly apart and large-scale cosmic structures wouldn't have formed. The Standard Model contains no suitable dark matter candidate. Neutrinos were once considered, but they're too light and move too fast to account for observations. Something else, something unknown, comprises the bulk of matter in the cosmos. The LHC searches for dark matter through multiple approaches. If dark matter particles interact through any force besides gravity, even extremely weakly, high-energy collisions might produce them. They wouldn't be detected directly, since by definition they barely interact with ordinary matter, but their presence could be inferred from missing energy and momentum. When the total energy and momentum of detected particles don't match what went into the collision, something invisible must have carried away the difference. Carefully analyzing these missing energy signatures and comparing them to backgrounds from known processes like neutrino production could reveal dark matter creation. Various theoretical frameworks propose dark matter candidates with different properties. Weakly interacting massive particles, or WIMPs, were long favored because their predicted interaction strength naturally produces the observed cosmic abundance through early universe thermodynamics. Supersymmetric theories, which propose that every standard model particle has a heavier partner, offer a natural WIMP candidate in the lightest supersymmetric particle. The LHC has searched extensively for signs of supersymmetry, but so far, no evidence has emerged. This doesn't rule out supersymmetry entirely, since the theory contains many free parameters and the superpartners might be heavier than the LHC can produce, but it has prompted theorists to consider alternative possibilities. Axions represent another dark matter candidate, originally proposed to solve a different problem in quantum chromodynamics, but potentially produced abundantly in the early universe. These hypothetical particles would be extremely light and weakly interacting, requiring different detection strategies than WIMPs. While the LHC isn't optimized for finding axions, other experiments at CERN and elsewhere employ resonant cavities and strong magnetic fields to search for these elusive particles. Dark photons, which would be partners to ordinary photons but with small mass, offer yet another possibility, and fixed-target experiments at CERN have searched for them by looking for unusual decays and interactions. The relationship between the LHC's energy scale and the scales relevant to dark matter and dark energy presents both opportunities and challenges. Dark matter particles, if they exist and interact through forces related to those in the standard model, might be produced at collision energies the LHC can achieve. But dark energy, the mysterious component causing the universe's accelerated expansion, operates on cosmological scales and energy densities many orders of magnitude lower than particle physics experiments can probe directly. Understanding dark energy likely requires integrating observations from astronomy and cosmology with insights from particle physics. Recognizing that the vacuum energy density implied by quantum field theory differs from the observed cosmological constant by an embarrassingly large factor. Extra dimensions beyond the familiar 3 of space and 1 of time appear in various theoretical frameworks attempting to unify gravity with the other forces. If these extra dimensions exist but are compactified at small scales, they might affect high-energy collisions in detectable ways. Some scenarios predict that gravity becomes much stronger at short distances, potentially allowing mini black holes to form in the most energetic LHC collisions. These microscopic black holes would evaporate almost instantly through Hawking radiation, producing distinctive signatures of multiple particles emerging from a single point. Despite searches, no evidence of such black hole production has appeared, placing constraints on how large extra dimensions could be and how they might be configured. String theory, perhaps the most prominent candidate for a quantum theory of gravity, suggests that fundamental particles aren't point-like but rather tiny vibrating strings. Different vibrational modes correspond to different particles, and the theory naturally incorporates gravity while potentially explaining the multitude of particles and forces we observe. However, string theory operates at energy scales called the Planck scale, roughly 1,000,000 billion times higher than the LHC can reach. Direct tests seem impossible with current or foreseeable technology. Yet string theory makes predictions about the structure of particle physics at lower energies, and deviations from standard model predictions in precision measurements might offer indirect evidence for or against various string theory scenarios. The detector's ability to distinguish between particles relies on understanding how different particle types interact with matter. Photons convert to electron-positron pairs in material, creating electromagnetic showers that deposit energy in calorimeters. Electrons and positrons similarly create showers, while also leaving tracks in tracking detectors. Muons, being heavier cousins of electrons, penetrate much deeper through matter, passing through calorimeters and registering only in the outermost muon chambers. Hadrons like protons, neutrons, and pions interact via the strong force, creating hadronic showers with different characteristics than electromagnetic ones. So neutrinos pass through the entire detector apparatus without interacting, carrying away energy that appears as missing in the event reconstruction. Tau leptons, the heaviest of the 3 charged lepton types, decay so quickly that they travel only about a millimeter before transforming into lighter particles. Identifying tau leptons requires recognizing their decay signatures, either a single charged particle plus neutrinos or three charged particles plus neutrinos. The challenge lies in distinguishing these signatures from the far more common jets of hadrons produced when quarks and gluons fragment. Advanced algorithms incorporating tracking information, calorimeter deposits, and particle identification help separate genuine tau leptons from backgrounds, essential for searches where taus might appear preferentially. Jets, the collimated sprays of particles produced when quarks or gluons emerge from collisions, carry information about the original pattern that created them. Jet substructure analysis examines the pattern of particles within jets, identifying features that might indicate whether a jet originated from a light quark, a bottom quark, a top quark, or a gluon. Since the top quark decays before it can form bound states, it produces a characteristic pattern of decay products that can be reconstructed even when the top quark carries enormous momentum and its decay products merge into a single jet. Similar techniques identify jets from highly boosted W and Z bosons, or Higgs bosons, opening windows into processes that would otherwise be obscured. B physics experiments at the LHC, particularly LHCb, occupy a unique niche between high-energy discovery physics and precision measurements. Rather than maximizing collision energy, LHCb optimizes for detecting particles containing bottom quarks, which are copiously produced even at relatively modest energies. The detector's forward geometry captures B hadrons that fly predominantly in the direction of the colliding beams, and its excellent vertex resolution allows precise measurement of decay positions and lifetimes. These capabilities enable studies of CP violation, rare decays, and mixing phenomena with unprecedented statistical power. Certain B meson decays occur extraordinarily rarely in the Standard Model, with branching ratios of 1 in billions or less. New physics beyond the Standard Model might enhance these rates or modify the angular distributions of decay products. LHCb has measured several rare decays that show intriguing hints of deviation from Standard Model predictions, though none yet reach the threshold of definitive discovery. The decay of BS mesons to pairs of muons, for instance, was measured after years of searching and found to match Standard Model expectations, constraining scenarios like supersymmetry that might have enhanced the rate. Other measurements, such as certain angular observables in B meson decays to K mesons and lepton pairs, show patterns that could suggest new particles entering through quantum loops, though alternative explanations remain possible. Quark flavor physics explores how quarks transform from one type to another, processes mediated by the weak force. The CKM matrix, named for Kabibo, Kobayashi, and Maskawa, describes the mixing between quark mass states and weak interaction states. Measuring the elements of this matrix through various decay processes provides consistency checks of the Standard Model and searches for new physics. Small inconsistencies in the CKM matrix's unitarity or unexpected patterns in flavor-changing transitions could reveal new particles or interactions not included in current theories. Charm quarks, lighter cousins of bottom quarks, also undergo mixing and CP violation, though at levels predicted to be much smaller in the Standard Model. LHCb has made precision measurements of charm-changing processes, observing direct CP violation in charm decays for the first time. These measurements test whether the same mechanisms responsible for CP violation in the bottom sector also operate in charm, or whether additional sources might exist. The interplay between different quark flavors and the patterns of their interactions build a detailed picture of how the fundamental forces operate and where new physics might hide. Neutrinos, the most enigmatic particles in the Standard Model, barely interact with matter despite being produced in vast numbers by the Sun, cosmic rays, and radioactive decay. They come in three flavors corresponding to the three charged leptons, and they oscillate between flavors as they travel, a phenomenon that requires them to have mass despite being massless in the original Standard Model. Experiments at CERN and elsewhere have measured the parameters governing neutrino oscillations with increasing precision. By determining the mass differences between neutrino types and the mixing angles that describe how their flavor and mass states relate. The absolute masses of neutrinos remain unknown, with experiments providing only upper limits and differences between mass states. Whether neutrinos are their own antiparticles, so-called Majorana particles, or distinct from their antiparticles like other fermions, remains an open question with profound implications. Neutrinoless double beta decay, a hypothetical process that could occur only if neutrinos are Majorana particles, would signal physics beyond the standard model and might help explain the universe's matter-antimatter asymmetry through a mechanism called leptogenesis. While experiments searching for this decay operate independently of CERN, the broader neutrino physics program informs and connects with the questions explored at the LHC. The strong force that binds quarks exhibits a property called asymptotic freedom, meaning quarks interact weakly at very short distances or high energies, but strongly at larger distances. This behavior, opposite to electromagnetism where charges interact more strongly at short range, emerges from the mathematics of quantum chromodynamics. At the highest energies the LHC achieves, quarks and gluons behave almost as free particles, allowing calculations using perturbative techniques. As collision products separate and cool, however, the strong force reasserts itself, confining quarks into hadrons through processes that remain difficult to calculate from first principles. Heavy ion collisions at the LHC recreate conditions of extreme temperature and density that last existed microseconds after the Big Bang. Rather than colliding protons, experimenters accelerate lead nuclei and smash them together, producing fireballs where thousands of particles interact simultaneously. In these collisions, matter briefly exists as a quark-gluon plasma, a state where quarks and gluons move freely rather than being confined in hadrons. The ALICE detector specializes in studying these collisions, measuring how the plasma flows and evolves before cooling into ordinary hadrons. Quark-gluon plasma exhibits surprising properties that have reshaped our understanding of quantum chromodynamics. Rather than behaving like a weakly interacting gas, as some early predictions suggested, the plasma flows like a nearly perfect fluid with extremely low viscosity. This collective behavior emerges from strong interactions between quarks and gluons, even at high temperatures. Jets of high-energy particles passing through the plasma lose energy in characteristic patterns, a phenomenon called jet quenching that provides insights into the plasma's properties. Measurements of how particles correlate in azimuthal angle reveal asymmetries driven by the initial collision geometry and subsequent fluid dynamics. Connecting observations from heavy ion collisions to theoretical predictions requires sophisticated simulations incorporating hydrodynamics, quantum chromodynamics, and transport theory. These simulations must account for how the colliding nuclei's initial conditions, including fluctuations in the positions of constituent nucleons, translate into the plasma's initial energy density distribution. They must describe how the plasma expands and cools, how collective flow develops, and how the transition from quarks and gluons to hadrons occurs. Comparing simulations to data allows extraction of fundamental properties like the shear viscosity to entropy density ratio, constraining our understanding of strongly coupled quantum systems. The temperatures achieved in heavy ion collisions, over 100,000 times hotter than the Sun's core, test whether phase transitions occur in nuclear matter and how the transition from confined to deconfined quarks manifests. So lattice quantum chromodynamics calculations performed on powerful supercomputers predict a smooth crossover rather than a sharp phase transition at LHC energies, consistent with experimental observations. At higher densities, such as might exist in neutron star cores, calculations suggest more complex behavior, including possible color superconducting phases, though accessing these conditions experimentally remains beyond current capabilities. Precision timing measurements enhance the detector's capabilities in numerous ways. The recent addition of timing layers to ATLAS and CMS, capable of measuring particle arrival times with precision around 30 picoseconds, helps distinguish between particles from different collisions occurring within the same bunch crossing. As the LHC increases its luminosity, and delivering more collisions per second, multiple proton-proton interactions occur each time bunches cross. Without timing information, particles from these pile-up collisions blend together, complicating event reconstruction. Precise timing associates particles with their originating collision, clarifying what happened in events of interest. Radiation damage poses ongoing challenges for detector components, especially those closest to the collision points where particle fluxes are highest. Over years of operation, detector materials accumulate damage that degrades performance, requiring periodic replacement of the most affected components. Silicon tracking detectors gradually lose efficiency as radiation creates defects in the crystal structure. Radiation-hard electronics designed to withstand the harsh environment still suffer eventual degradation. Planning for detector upgrades incorporates radiation tolerance as a key design criterion, using materials and fabrication techniques that minimize damage or recover more effectively. The high-luminosity LHC upgrade, scheduled to begin operation in the coming years, will increase collision rates by a factor of 5 to 7 beyond the current LHC's design luminosity. This massive increase in data will enable precision measurements of rare processes and enhance sensitivity to subtle deviations from standard model predictions. However, it also demands comprehensive detector upgrades to handle the higher particle rates, increased radiation doses, and greater pileup. New tracking detectors, calorimeter electronics, trigger systems, and data acquisition infrastructure represent years of development by international collaborations involving thousands of scientists and engineers. Trigger systems exemplify the challenge of extracting signals from noise. Only a tiny fraction of collisions produces potentially interesting physics, yet the LHC generates collisions at rates far exceeding what can be recorded and stored. Hardware-based Level 1 triggers make initial selections within microseconds, using coarse detector information to identify events with high-energy particles or unusual signatures. Events passing this first filter proceed to higher-level software triggers that reconstruct more detailed information and apply sophisticated selection criteria. The trigger algorithms must balance efficiency, avoiding rejection of rare new physics, against rate limitations imposed by computing and storage capacity. Machine learning techniques have transformed how physicists analyze LHC data. Neural networks and other algorithms can identify subtle patterns that distinguish signal from background more effectively than traditional cut-based selections. They can classify jets according to their origin, reconstruct complex event topologies, and even help correct for detector effects. Some applications use simulation to train algorithms, while others employ data-driven techniques to avoid biases from imperfect modeling. The integration of machine learning extends beyond analysis to detector operation, trigger decisions, and real-time data quality monitoring. Quantum chromodynamics calculations face challenges from the theory's strong coupling at low energies, where perturbative methods break down. Lattice QCD, which discretizes spacetime and solves the theory numerically, provides predictions for hadron masses, decay constants, and other quantities that can be compared to experimental measurements. These calculations require enormous computational resources, and uncertainties from finite lattice spacing, finite volume effects, and quark mass extrapolations must be carefully controlled. As lattice calculations improve and experimental measurements become more precise, tensions between theory and experiment might reveal new physics or highlight where current approaches need refinement. Parton distribution functions describe how a proton's momentum divides among its constituent quarks and gluons as a function of the proton's momentum fraction each carries. When these distributions can't be calculated from first principles in QCD, but must be determined from experimental data, particularly from deep inelastic scattering experiments, where high-energy electrons probe proton structure. The LHC's proton-proton collisions depend on these distributions, since the collision energy available for particle production depends on the momentum fractions of the colliding partons. The structure functions themselves evolve with the energy scale of the collision through equations that describe how quarks and gluons radiate and split as the resolution of the probe increases. At higher energies, the proton appears to contain more partons, particularly gluons, which proliferate through QCD processes. But this scaling behavior provides one of the most stringent tests of quantum chromodynamics and demonstrates that what we observe depends fundamentally on the energy scale at which we examine nature. When protons collide at the LHC, the actual hard interaction occurs between individual partons rather than between the protons as whole objects. A quark from one proton might scatter off a gluon from another, or two gluons might annihilate to produce a pair of heavy particles. The collision energy available for this elementary process is just a fraction of the total beam energy, determined by the momentum fractions carried by the participating partons. Most of the time, the partons involved carry relatively small momentum fractions, meaning the effective collision energy is much less than the 14 tera-electron volts available in the center of mass frame. Only occasionally do high momentum partons collide, producing the spectacular high-energy events that physicists seek. This statistical nature of proton collisions means that even rare processes can be explored by colliding enough protons together. The LHC achieves this through its extraordinary luminosity, measured in terms of particles per square centimeter per second. Higher luminosity means more collisions per unit time, giving experimenters more chances to catch rare events. The machine operates by colliding bunches of protons rather than individual particles. Each bunch contains around 100 billion protons, and when two bunches cross, dozens of separate collisions can occur simultaneously. This pileup of events creates a tremendous challenge for the detectors, which must disentangle multiple simultaneous interactions to identify the one event of interest among the many mundane scatters. The four major detectors at the LHC represent different philosophies and priorities in particle physics research. ATLAS and CMS are general-purpose detectors designed to search for new phenomena across a broad range of physics processes. Both are massive instruments, several stories tall and weighing thousands of tons, built around the collision points with cylindrical symmetry to capture particles emerging in all directions. Despite their similar goals, the two experiments employ different technical solutions and serve as independent checks on each other's findings. The discovery of the Higgs boson required confirmation from both detectors, ensuring that the observed signal wasn't an artifact of a particular detector design or analysis method. ATLAS, the larger of the two, stretches 46 meters in length and 25 meters in height, making it the biggest volume particle detector ever constructed. Its name refers to the massive toroidal magnets that bend the paths of charged particles, allowing momentum measurements. These air-core toroids avoid the need for tons of iron yokes while providing a powerful magnetic field in the muon detection system. Closer to the beam pipe, a separate solenoid magnet surrounds the inner tracker and calorimeters, bending particle trajectories in that region. Now, this complex arrangement of magnetic fields allows precise measurement of particle momenta across a wide range. The ATLAS inner detector sits closest to the collision point, operating in an intense radiation environment where silicon sensors track charged particles with micrometer precision. Multiple layers of pixel and strip detectors record the positions where particles pass through, allowing reconstruction of their trajectories back to the collision point. This precision tracking enables identification of particles that decay a millimeter or so from the primary collision, revealing the presence of short-lived particles such as bottom quarks. Beyond the inner tracker, electromagnetic and hadronic calorimeters measure particle energies by absorbing them completely, causing cascades of secondary particles that deposit energy in layers of active material. The outermost layers contain the muon spectrometer, tracking these penetrating particles through huge volumes instrumented with chambers that record their passage. CMS takes a different approach with a more compact design centered around a superconducting solenoid that generates a magnetic field of nearly 4 Tesla, among the strongest used in any detector. This intense field is confined within a return yoke made of thousands of tons of iron, which also serves as the absorber for the hadronic calorimeter. The entire detector has a more integrated design where magnetic field, calorimetry, and muon detection work together in a unified structure. Like ATLAS, CMS features a silicon tracker at its core, but uses a different crystal-based electromagnetic calorimeter that provides excellent energy resolution for photons and electrons. The crystals themselves are an engineering marvel, grown with exceptional purity and machined to precise specifications, then read out with photodetectors that can register individual photons of scintillation light. Both detectors must handle data rates that would overwhelm any conceivable storage system if every collision were recorded. At the LHC's peak luminosity, collisions occur at a rate of 40 million per second, with each event generating megabytes of raw data from the millions of detector channels. Storing everything would require petabytes of data per second, an impossible task even for modern computing infrastructure. Instead, The detectors employ sophisticated trigger systems that make split-second decisions about which events might be interesting enough to keep. Hardware triggers examine each collision in microseconds, looking for basic signatures like high-energy particles or unusual patterns. Events that pass this first stage proceed to software triggers running on thousands of processors, where more refined analysis decides whether to write the data to permanent storage. Ultimately, only a few hundred events per second survive this selection process, but they represent the most promising candidates for new physics. The LHCb detector specializes in studying particles containing bottom quarks, focusing on subtle differences between matter and antimatter. Rather than surrounding the collision point, LHCb is built as a forward spectrometer, instrumenting only the region where collision products emerge in roughly the same direction as the beam. This geometry takes advantage of the fact that heavy quarks produced in proton collisions tend to be boosted forward or backward rather than emerging at large angles. By concentrating instrumentation in this region, LHCb achieves exceptional precision in reconstructing particle decays while using less detector volume than the general-purpose experiments. The physics motivation for LHCb centers on the observed matter-antimatter asymmetry in the universe. In the immediate aftermath of the Big Bang, matter and antimatter should have been created in equal amounts, yet the universe we observe consists almost entirely of matter. Something must have caused this imbalance, and physicists believe it relates to small differences in how matter and antimatter behave. These differences, called charge parity violations, have been observed in systems containing strange quarks and bottom quarks, but the known effects are far too small to explain the cosmic asymmetry. LHCb searches for larger violations that might point toward new physics beyond the standard model, examining thousands of different decay modes of particles containing heavy quarks and comparing them to their antimatter counterparts. The detector achieves this through precision vertex reconstruction and identifying exactly where particles decay relative to the primary collision point. Bottom quarks live long enough to travel a few millimeters before decaying, producing secondary vertices displaced from the main collision. By measuring these decay positions with extreme precision, LHCb can reconstruct complex decay chains and measure particle lifetimes. The detector also includes systems for identifying different particle types, distinguishing electrons from pions, muons from kaons, and so forth. This particle identification uses several techniques including measurements of Cherenkov radiation, the optical equivalent of a sonic boom that occurs when particles move faster than light travels through a medium. ALICE, the fourth major LHC detector, pursues entirely different physics by studying collisions of lead nuclei rather than protons. While proton collisions explore high-energy interactions of a few partons, heavy ion collisions create conditions of extreme temperature and density where thousands of particles are produced simultaneously. These collisions recreate conditions that existed microseconds after the Big Bang, when the universe was so hot and dense that quarks and gluons existed freely rather than being confined inside hadrons. The resulting state of matter, called quark-gluon plasma, represents a phase transition in quantum chromodynamics analogous to ice melting into water. Creating and studying this primordial state of matter requires collision energies that can overcome the binding energy of atomic nuclei and heat a substantial volume of space to temperatures exceeding 1 trillion degrees. Lead ions accelerated to nearly light speed carry enormous energy, and when they collide, that energy is deposited into a region of space smaller than a proton, creating extremely high energy densities. The resulting fireball expands and cools, undergoing a phase transition back to ordinary hadronic matter within about 24 seconds. During its brief existence, the quark-gluon plasma exhibits properties of a near-perfect fluid with extremely low viscosity, flowing and expanding according to hydrodynamic equations. ALICE is optimized to handle the thousands of particles emerging from each heavy ion collision, a far more complex environment than typical proton collisions. The detector includes a large time projection chamber that tracks charged particles through a volume filled with gas, recording their three-dimensional trajectories as they ionize the gas along their paths. This allows reconstruction of the collision event in its full complexity, revealing patterns in how particles emerge collectively rather than individually. The detector also measures photons and identifying particles over a wide range of momenta, from soft particles produced thermally in the fireball to hard particles created in the initial collision before the plasma forms. The transition from confined quarks to deconfined plasma manifests in several experimental signatures: jets of particles. The collimated sprays that result from high-energy quarks or gluons are suppressed in heavy ion collisions compared to proton collisions. This quenching occurs because the high-energy partons lose energy as they traverse the dense plasma, radiating away their momentum through interactions with the medium. By measuring this suppression, physicists probe the properties of the plasma itself. Similarly, heavy quark-antiquark pairs called quarkonia show suppressed production in the plasma due to screening of the color force, analogous to how electric charge is screened in a plasma of charged particles. Beyond these four major detectors, several smaller experiments pursue specialized physics at the LHC. Totem measures elastic scattering where protons remain intact, approaching the beam very closely to catch particles that scatter at tiny angles. This provides information about the proton's size and structure at very small distance scales. LHCF studies particles produced in the extreme forward direction to understand cosmic ray interactions in the atmosphere, while Mo et al. Searches for magnetic monopoles and other exotic, highly ionizing particles that might be produced in high-energy collisions. The Higgs boson discovery in 2012 represents the LHC's most celebrated achievement, confirming the existence of a particle predicted nearly 50 years earlier to explain how other fundamental particles acquire mass. The Brout-Englert-Higgs mechanism, as it is formally known, proposes that space is filled with a field that interacts with particles as they move through it. This field, unlike all others in the Standard Model, has a non-zero value in its lowest energy state. Particles acquire mass through their coupling to this field, with stronger coupling producing heavier particles. The Higgs boson is the quantum excitation of this field, the ripple that remains after energy is deposited into it. Searching for the Higgs required looking for a particle whose properties were predicted but whose mass was unknown. The Standard Model doesn't specify the Higgs mass, though various theoretical and experimental constraints suggested it should lie somewhere between about 100 and 1,000 times the proton mass. This wide range meant that finding the Higgs required systematic searches across many possible masses and many different decay modes. A light Higgs decays primarily to bottom quark pairs, but this signal is nearly impossible to distinguish from background processes that produce bottom quarks copiously. More distinctive decay modes include decays to pairs of photons, to two Z bosons, or to pairs of W bosons, though these occur less frequently. The search focused on looking for excesses of events at a particular mass across multiple channels simultaneously. If the Higgs exists with a certain mass, it should appear as a peak in the invariant mass distribution of its decay products. Two photons coming from a Higgs decay, for instance, should have a total energy and momentum corresponding to the Higgs mass. By reconstructing events with two high-energy photons and plotting their invariant mass, experimenters could search for a bump above the smooth background from other processes. Similarly, searches in the 4-lepton channel looked for events where two Z bosons decayed to electron or muon pairs, again seeking an excess at some mass value. The announcement in July 2012 revealed that both ATLAS and CMS had observed a new particle near 125 times the proton mass with properties consistent with the Higgs boson. The statistical significance exceeded 5 sigma, the physics community's threshold for claiming a discovery. This meant the probability that random fluctuations could produce such a signal was less than 1 in 3 million, essentially ruling out chance as an explanation. Subsequent measurements confirmed that the particle's properties matched predictions for the Standard Model Higgs. It decayed to the expected particles with the expected rates, and its spin and parity quantum numbers matched the theoretical expectations. Yet even with the Higgs discovered, many questions remain. The measured mass lies in an interesting range that suggests the universe might be in a metastable state, stable for now, but not representing the true minimum energy configuration. Quantum corrections from the heavy top quark create a potential energy landscape where the Higgs field could potentially tunnel to a different, lower energy state. This transition, if it occurred, would be catastrophic. fundamentally changing the properties of particles and invalidating the physics that allows complex structures to exist. Calculating whether our vacuum is truly stable requires precise knowledge of particle masses and coupling constants, parameters that the LHC continues to measure with increasing accuracy. The Higgs also plays a role in one of physics' deepest puzzles. Why is the hierarchy between the electroweak scale and the Planck scale so enormous? The Higgs mass receives quantum corrections from virtual particles at all energy scales, and naively, these corrections should drive the mass up to the Planck scale unless some mechanism exists to cancel them. This fine-tuning problem suggests that new physics should appear around the electroweak scale to stabilize the Higgs mass. Supersymmetry offers one solution by introducing partner particles whose contributions to quantum corrections cancel those of known particles. The LHC has searched extensively for supersymmetric particles, but has found no evidence for them, constraining or ruling out many proposed models. Dark matter searches at the LHC proceed through multiple strategies, all based on the assumption that dark matter particles might be produced in high-energy collisions if they have masses accessible to the machine. The most direct signatures involve missing transverse energy, where momentum appears not to be conserved because unseen particles carry it away. Events with a single energetic jet and large missing energy could signal dark matter production if the jet arises from initial state radiation and the missing energy represents a pair of dark matter particles. Similarly, events with single photons or single W or Z bosons plus missing energy provide potential dark matter signatures. These searches must contend with standard model backgrounds that naturally produce missing energy, particularly from neutrinos that escape detection. Distinguishing dark matter from neutrino production requires careful analysis of event kinematics and the development of sophisticated statistical techniques. Experimenters look for subtle differences in the distributions of various measured quantities that might indicate a new particle rather than just more neutrinos. The absence of clear signals sets limits on how strongly dark matter might interact with ordinary matter, constraining theoretical models even when no discovery is made. Alternative approaches search for dark matter through its effects on visible particles. If dark matter couples to quarks or gluons, it might modify the production rates of various standard model particles. Precision measurements of top quark production, for instance, could reveal anomalies if dark matter particles contribute to the processes. Similarly, searches for resonances in pairs of particles might reveal heavy dark matter particles that decay to standard model states. These signatures differ from the missing energy searches and provide complementary information about dark matter's possible properties. The search for supersymmetry has evolved considerably since the LHC began operations. Early searches focused on simplified models where supersymmetric particles would decay through short chains to produce distinctive signatures with multiple jets and large missing energy. The absence of signals in these channels has pushed the mass limits for some supersymmetric particles above 2 tera-electron-volts, far heavier than the originally favored range. This has motivated searches for more complex scenarios where supersymmetric particles might evade detection by decaying differently, or by having more compressed mass spectra where decay products carry less energy. Long-lived particles represent one such alternative signature. If the lightest supersymmetric particle is nearly degenerate in mass with heavier supersymmetric states, decays between them release little energy and might take a long time to occur. The resulting particles could travel through the detector before decaying, producing unusual signatures like tracks that appear in the outer detector layers without corresponding hits in the inner tracker, or energy deposits in calorimeters arriving late compared to particles from the primary collision. Yet searching for these exotic signatures requires techniques quite different from standard searches and has opened new experimental territory. The study of antimatter at the LHC proceeds primarily through heavy ion collisions and specialized experiments at CERN's lower energy facilities. The ALICE detector has observed the production of antimatter nuclei, including anti-helium-3 and even hints of anti-helium-4, the heaviest antimatter nuclei ever created. These exotic objects form when multiple antiquarks happen to combine in the fireball of a heavy ion collision, a rare occurrence given that the antiquarks must find each other and bind before the expanding system becomes too dilute. The production rates provide information about the thermodynamic conditions in the quark-gluon plasma and test models of how composite particles form from quarks. More detailed studies of antimatter occur at the antiproton decelerator complex, where antiprotons from the accelerator chain are slowed to very low energies and combined with positrons to create anti-hydrogen atoms. The alpha experiment traps these anti-atoms using magnetic fields and studies their properties with unprecedented precision. Comparing the properties of hydrogen and anti-hydrogen tests, one of physics' most fundamental symmetries, charge parity time reversal invariance, which demands that matter and antimatter behave identically aside from the sign of their charges. Any difference would signal new physics and might provide clues to understanding the cosmic matter-antimatter asymmetry. Recent measurements have shown that anti-hydrogen responds to gravity in the same way as ordinary matter, falling downward rather than upward, confirming that antimatter has normal gravitational mass. Spectroscopic measurements comparing energy levels in hydrogen and anti-hydrogen have achieved extraordinary precision, finding no differences within experimental uncertainty. These null results strengthen confidence in fundamental symmetries while also improving the limits on possible violations. The experiments require extraordinary technical sophistication, so maintaining anti-hydrogen atoms in magnetic traps at temperatures near absolute zero for extended periods, while making precision measurements without destroying the fragile anti-atoms. Exotic hadrons containing multiple heavy quarks represent another frontier being explored at the LHC. While ordinary mesons contain one quark and one antiquark, and ordinary baryons contain 3 quarks, quantum chromodynamics allows more complex bound states. Tetraquarks with 4 quarks, pentaquarks with 5, and glue balls made purely of gluons are all theoretically possible, though their properties and even their existence as distinct states have been debated. The LHCb experiment has discovered several candidates for such exotic states, including structures in the spectrum of particles containing charm quarks that don't fit the pattern of conventional quark combinations. The X3872, discovered earlier at other facilities but studied in detail at LHCb, represents a tetraquark candidate with properties that challenge theoretical understanding. Its mass lies extremely close to the threshold for producing a D meson and a D star meson together, suggesting it might be a loosely bound molecule of these two mesons rather than a tightly bound 4-quark state. Distinguishing between these scenarios requires precise measurements of how the state decays and how its properties depend on the environment, ongoing research that pushes the boundaries of quantum chromodynamics calculations. More recently, LHCb announced evidence for pentaquarks, the 5-quark bound states appearing in the decay of bottom baryons. These structures appear as resonances in the spectrum of particles emerging from the decay, indicating that intermediate states with specific masses and quantum numbers are formed. Whether these represent genuine 5-quark bound states or merely molecular arrangements of conventional hadrons remains under investigation. The discoveries highlight how much remains to be learned about how quarks combine and bind even within the framework of the established theory. The precision frontier complements the energy frontier in testing the standard model and searching for new physics, while discovering new particles requires pushing to higher energies. And subtle deviations in the properties and interactions of known particles can also reveal new physics through their quantum corrections. The LHC serves as a precision instrument for measuring properties like the top quark mass, the strong coupling constant, and various branching ratios and production cross-sections. These measurements have achieved remarkable accuracy, testing quantum chromodynamics and electroweak theory at the per-mil level, or better in some cases. The top quark, the heaviest known elementary particle, at about 173 times the proton mass, decays before it can form bound states, allowing direct study of a bare quark's properties. Its large mass means it couples most strongly to the Higgs field, making precision measurements of top quark properties particularly sensitive to Higgs physics and potential new particles. The LHC produces top quarks copiously, both in pairs through the strong force and singly through electroweak interactions, providing multiple channels for detailed study. Measurements of the top quark mass have achieved precision better than 0.5%, incorporating sophisticated techniques to account for how quarks appear as jets in the detector and how the mass is defined theoretically. The most precise measurements combine information from different decay channels and use advanced analysis techniques, including matrix element methods that calculate the probability of each observed event arising from specific top quark properties. This precision matters because the top quark mass, together with the Higgs mass and W boson mass, determines quantum corrections throughout the Standard Model and affects predictions for various processes. The relationship between these three fundamental masses creates what physicists call the electroweak fit. When researchers plug measured values into theoretical equations, they can predict what other quantities should be if the Standard Model is correct. Any significant deviation between prediction and measurement would signal new physics. So far, the measurements align remarkably well with Standard Model expectations, but the precision keeps improving, and future measurements might reveal tiny discrepancies that point towards something beyond. The production of top quarks at the LHC happens in several different ways. The most common involves two gluons colliding and creating a top-antitop pair, but single top quarks can also be produced through different processes involving the W boson. Each production mechanism provides different information. The single top production rate, for instance, directly measures something called the VTB matrix element, which describes how the top quark transforms into a bottom quark through weak interactions. These measurements confirm that the top quark couples to the bottom quark with nearly maximal strength, as the Standard Model predicts. Beyond standard top quark physics, researchers search for more exotic phenomena. What if top quarks could be produced in association with other unexpected particles? What if their decay pattern showed rare processes that happen less frequently than predicted? Teams scan through collision data, looking for events where a top quark appears alongside additional high-energy photons, Z bosons, or even Higgs bosons. Top Higgs-associated production is particularly interesting because it directly probes how the top quark interacts with the Higgs field. Since the top quark has the largest coupling to the Higgs, any new physics affecting that coupling might show up first in top Higgs events. The study of rare top quark decays opens another window. While top quarks almost always decay to W bosons and bottom quarks, quantum mechanics allows for rare alternative paths. A top quark might occasionally emit a Z boson or a photon while decaying. These processes are predicted to happen in maybe 1 out of every 1,000 or 10,000 decays, making them challenging to observe. But when researchers do measure these rare decays, they're testing predictions that depend on the quantum structure of the Standard Model. New particles or forces could alter these rates. One particularly intriguing possibility involves top quarks decaying into lighter quarks in ways forbidden by the Standard Model. If a top quark occasionally transformed into a charm quark through a process that violates flavor conservation, it would be revolutionary. Teams search for these forbidden decays, setting increasingly strict limits on how often they could occur. So far, no evidence has emerged, but the searches continue with ever-growing datasets. Moving into even more speculative territory, physicists consider whether top quarks might interact with dark matter. If dark matter particles can interact with ordinary matter through some undiscovered force, top quarks seem like promising candidates for mediating that interaction given their large mass. Researchers design searches where proton collisions would produce a top-antitop pair, along with missing energy carried away by invisible dark matter particles. The challenge lies in distinguishing this signal from numerous other processes that also produce top quarks and genuine missing energy from neutrinos. The LHC's antimatter research extends beyond specific particle studies into broader questions about matter-antimatter asymmetry. Our universe appears to contain almost entirely matter, with very little antimatter. Yet when energy converts into particles in the laboratory, matter and antimatter appear in equal amounts. Something must have happened in the early universe to create this imbalance. Physicists suspect that subtle differences in how matter and antimatter behave under weak interactions might be responsible, but the differences observed so far aren't large enough to explain the universe's composition. The LHCb experiment specializes in studying these matter-antimatter differences through beauty quarks. When particles containing beauty quarks decay, they sometimes show different behavior depending on whether they're made of matter or antimatter. These differences, called CP violation, have been measured in several systems. The LHCb detector is designed specifically to catch the particles that emerge at small angles from the collision point, which is where beauty quark particles typically go. Why its precise tracking and particle identification capabilities allow researchers to reconstruct complex decay chains and measure tiny asymmetries. One remarkable measurement involves particles called beauty mesons that can oscillate between matter and antimatter states. A particle might be created as matter, spontaneously convert to antimatter, then flip back to matter, all before it decays. The quantum mechanics governing these oscillations allows for CP violation, and LHCb has measured the relevant parameters with extraordinary precision. Some measurements reach fractional uncertainties below 1%, representing decades of experimental refinement. The study of charm quarks provides complementary information. Charm quarks are lighter than beauty quarks, and CP violation in charm systems is predicted to be smaller. For a long time, no significant CP violation had been observed in charm decays. Then, in recent years, LHCb reported evidence for CP violation in certain charm meson decays. The effect is small, just a fraction of a percent difference between matter and antimatter decay rates, but statistically significant. This discovery opened a new area for testing the standard model and searching for anomalies. These precision measurements connect to broader questions about the universe's evolution. During the first microseconds after the Big Bang, when temperatures exceeded trillions of degrees, all these particles and their antiparticles existed in a hot plasma. As the universe expanded and cooled, most matter and antimatter annihilated, leaving behind the slight excess of matter that became everything we see today. Understanding exactly how that excess arose requires knowing all possible sources of CP violation and whether they're sufficient to explain observations. Some theories propose additional sources of CP violation beyond what the standard model contains. These might involve new particles or forces that appeared only at extremely high energies present in the early universe. While those conditions can't be recreated directly at the LHC, their effects might leave subtle fingerprints in how particles behave today. Discrepancies between measured CP violation and standard model predictions could hint at these hidden influences. The experimental techniques for studying antimatter at CERN include more than just collision experiments. The alpha and base experiments work with trapped antihydrogen atoms, studying their properties directly. Creating antihydrogen requires combining antiprotons from the antiproton decelerator with positrons, then cooling the resulting antiatoms to temperatures approaching absolute zero. Magnetic traps hold these antiatoms suspended in vacuum, isolated from any ordinary matter that would cause immediate annihilation. Why go through such extraordinary effort? Because comparing hydrogen and antihydrogen provides a fundamental test of CPT symmetry, the combined operation of charge conjugation, parity inversion, and time reversal. According to quantum field theory, this combined symmetry must be exact. If antihydrogen behaved differently from hydrogen in any measurable way, it would overturn fundamental theoretical principles. Teams have measured the antihydrogen spectrum with remarkable precision, comparing the frequencies of light absorbed by antihydrogen atoms to those absorbed by hydrogen. So far, the two are identical within experimental uncertainty, but each improvement in precision provides a more stringent test. Beyond hydrogen spectroscopy, researchers measure other antihydrogen properties, including how it responds to gravity. Does antimatter fall down like ordinary matter, or could it fall up? The latter possibility seems absurd based on current theory, but it's never been tested directly with neutral antimatter. Alpha has reported preliminary measurements showing antihydrogen falling downward as expected, but with large uncertainties. More precise experiments are underway to measure the gravitational acceleration of antimatter with greater accuracy. The quest to understand dark matter and dark energy represents perhaps the most profound mystery facing physics today. Evidence from astronomy overwhelmingly indicates that the matter we can see constitutes only about 5% of the universe's total energy content. Dark matter makes up another 27%, and dark energy accounts for the remaining 68%. Yet we have no idea what these components actually are at the microscopic level. The LHC contributes to dark matter searches in several ways. If dark matter consists of weakly interacting massive particles, then proton collisions might occasionally produce them. These particles would immediately leave the detector without interacting, carrying away energy and momentum. By looking for events where the visible particles appear to recoil against something invisible, researchers search for dark matter production. The challenges are substantial because many standard model processes also produce genuine missing energy through neutrinos, which also escape detection. Teams use various strategies to distinguish potential dark matter signals from backgrounds. They might look for events with a single high-energy jet recoiling against missing energy, or events with photons plus missing energy, or specific combinations of quarks and leptons accompanying the invisible particles. Each search targets different theoretical models of how dark matter might interact with ordinary matter. The LHC experiments have explored a vast range of parameter space, excluding many simple dark matter models, but not yet finding definitive evidence. Some theories propose that dark matter interacts with ordinary matter through a new force carried by particles called dark photons or mediators. These would be similar to photons, but coupled primarily to dark matter, with only weak interactions with standard model particles. Searches for dark photons look for unexpected resonances in events containing photons or lepton pairs. Other models suggest dark matter might be produced in decays of heavier particles created in collisions, and teams search for these complex signatures as well. The interplay between LHC searches and direct detection experiments provides complementary constraints. Direct detection experiments deep underground try to catch dark matter particles from space colliding with atomic nuclei. These experiments are sensitive to different aspects of dark matter interactions than the LHC. Together, the two approaches map out where dark matter could hide in the vast landscape of theoretical possibilities. As experimental sensitivity improves, the remaining allowed parameter space shrinks. Dark energy presents an even thornier problem. Unlike dark matter, which gravitationally affects how galaxies move and how cosmic structures form, dark energy appears to be driving the accelerated expansion of the universe itself. The simplest explanation is Einstein's cosmological constant, a uniform energy density filling all space. But calculating what this energy density should be from quantum field theory gives an answer larger than observations by a factor of 10 to the 120th power. This cosmological constant problem ranks among physics' greatest puzzles. The LHC can't directly detect dark energy, but it can test theories that attempt to explain it. Some proposals link dark energy to undiscovered particles or fields that become important only at cosmological scales. Others suggest modifications to gravity itself at large distances. While these ideas remain speculative, measurements of fundamental constants and particle properties at the LHC constrain what's possible. Any new particles or forces must be consistent with terrestrial experiments, even if their main effects appear cosmologically. The search for physics beyond the standard model extends in many directions simultaneously. Supersymmetry remains a compelling theoretical framework, despite the lack of experimental evidence so far. The idea that every known particle has a supersymmetric partner with different spin properties would solve several theoretical problems. It would help explain why the Higgs mass is as small as observed. It would unify the strengths of fundamental forces at high energies, and it would naturally provide a dark matter candidate. Early supersymmetry models predicted partner particles with masses accessible at the LHC, but searches have found nothing. This doesn't rule out supersymmetry entirely. The partner particles might be heavier than expected, beyond current LHC reach. Or supersymmetry might be realized in nature in more subtle ways than the simplest model suggested. Searches continue for various supersymmetric signatures, including events with many jets, leptons, and missing energy. Teams also look for specific superpartner particles like gluinos, squarks, and neutralinos using specialized analysis techniques optimized for each scenario. Extra dimensions provide another theoretical direction. What if our three-dimensional space is embedded in a higher dimensional geometry, with the extra dimensions curled up so small we don't notice them in everyday life? String theory predicts such extra dimensions, and some models suggest their effects might appear at LHC energies. Signatures could include excited states of quarks and leptons, the production of gravitons that escape into extra dimensions carrying away energy, or tiny black holes that form when particles collide with enough energy density concentrated in a small region. The black hole scenario is particularly striking. If extra dimensions lower the fundamental Planck scale, where gravity becomes strong, then particle collisions at the LHC might reach energies where black holes can form. These wouldn't be dangerous cosmic scale black holes. They'd be microscopic quantum objects that evaporate almost instantly through Hawking radiation. Detecting them would be revolutionary, providing direct evidence for quantum gravity effects. Searches look for events with unusual distributions of particles that might come from black hole formation and decay. So far, nothing has appeared, constraining how large extra dimensions could be. Other exotic possibilities include magnetic monopoles, which would be isolated magnetic charges, similar to how electrons carry electric charge, and quarks or leptons being composite objects made of even more fundamental constituents. Each idea leads to specific predictions that experimentalists can test. The absence of evidence for any of these phenomena doesn't mean they don't exist, but it does constrain the parameter space where theorists can build models. Quantum entanglement studies at the LHC represent a newer research direction. Entanglement, the strange quantum correlation where measuring one particle instantly affects another regardless of distance, is typically studied in carefully controlled atomic physics experiments. But entanglement should exist in the extreme conditions of particle collisions too. Researchers have recently demonstrated that top-anti-top pairs produced at the LHC are quantum entangled, showing correlations in their spin directions that exceed what classical physics allows. Measuring entanglement in top quark pairs required sophisticated analysis. Top quarks decay too quickly to be observed directly, so their spins must be inferred from the directions of their decay products. Teams studied the angular distributions of leptons coming from top and anti-top decays, finding patterns consistent with quantum entanglement. This represents the first observation of entanglement between the heaviest known fundamental particles and demonstrates that quantum effects survive even in the messy, high-energy environment of hadron collisions. Yet the implications reach beyond fundamental interest. Entanglement in top quark pairs could serve as a probe for new physics. Any additional particles or forces affecting top quark production might alter the entanglement properties. By measuring these quantum correlations precisely, researchers gain another handle on potential deviations from standard model predictions. It's an elegant example of how concepts from quantum information science intersect with high-energy physics. The technological achievements enabling these discoveries deserve recognition in their own right. Superconducting magnets at the LHC operate at 1.9 Kelvin, colder than outer space, using superfluid helium as coolant. Each magnet carries currents of about 11,000 amperes, generating magnetic fields exceeding 8 Tesla, over 100,000 times Earth's magnetic field. Thousands of these magnets bend particle beams around the ring's 27-kilometer circumference. The refrigeration system, handling 96 tons of liquid helium, represents one of the world's largest cryogenic installations. Detector technologies push boundaries across multiple domains. Silicon tracking detectors contain sensors with feature sizes comparable to advanced semiconductor manufacturing, arranged in layers that provide three-dimensional particle tracking with micron precision. Electromagnetic calorimeters use dense crystals that scintillate when particles pass through, with photodetectors reading out tens of thousands of channels. Hadron calorimeters absorb strongly interacting particles using alternating layers of absorber material and active sensors. Muon systems in the detector's outermost layers identify these heavy leptons that penetrate through all the other detector components. The data acquisition and computing challenges are staggering. Proton bunches collide every 25 nanoseconds when the LHC runs at design performance. Each crossing potentially produces dozens of simultaneous proton-proton collisions. The detectors generate millions of electronic signals for every bunch crossing. Custom-built trigger systems decide in microseconds which events are interesting enough to save. Even after aggressive filtering, experiments record thousands of events per second, each containing megabytes of information describing particle trajectories and energy deposits. Storing and analyzing this flood of data requires a globally distributed computing infrastructure. The worldwide LHC computing grid connects hundreds of computing centers across dozens of countries. Raw data flows from CERN to Tier 1 centers, then propagates to Tier 2 facilities where thousands of physicists access it for analysis. The total data storage for LHC experiments has grown to hundreds of petabytes. Analyzing it uses millions of CPU cores simultaneously running reconstruction and analysis algorithms. Machine learning has transformed how physicists extract information from this data. Neural networks trained on simulated collision events learn to identify specific particle types or recognize signatures of interesting processes. These algorithms often outperform traditional analysis methods, especially for complex signatures involving many particles. Researchers now routinely use deep learning for particle identification, on energy calibration, and even real-time event selection in the trigger systems. The collaborative nature of CERN research brings together scientists from dozens of countries. ATLAS and CMS each involve over 3,000 physicists from more than 40 nations. Smaller experiments still typically include hundreds of collaborators. These massive teams function through intricate organizational structures with working groups focused on different physics topics, detector components, and analysis techniques. Decision-making happens through consensus building, with results scrutinized through multiple layers of internal review before publication. This international cooperation happens despite political tensions and economic pressures. Scientists from countries with complex diplomatic relations work side by side in pursuit of shared scientific goals. The collaborative spirit that defines CERN represents an idealistic vision of what humanity can accomplish through joint effort. Young researchers from diverse backgrounds interact, forming professional networks and friendships that span the globe. Yet many physicists credit their CERN experience with broadening their perspectives beyond their home institutions and cultures. The future of CERN looks towards several major upgrades and new facilities. The high-luminosity LHC currently under construction will increase collision rates by a factor of 5 to 10. This means proportionally more data, allowing measurements of rare processes and improvements in precision. It also means harsher radiation environments and higher detector occupancies, requiring upgraded detectors with better radiation tolerance and faster readout electronics. Both ATLAS and CMS are replacing major detector components to handle these conditions. Beyond the LHC upgrades, CERN is studying options for a future circular collider, a 100-kilometer ring that could eventually collide protons at energies up to 100 TeV, 7 times higher than the LHC. The project would unfold in stages, first building an electron-positron collider in the new tunnel, then later adding proton collision capability. The electron-positron phase would produce millions of Higgs bosons, allowing ultra-precise measurements of its properties. The subsequent proton collider would extend the energy frontier, potentially discovering new particles well beyond current reach. Such ambitious projects require decades of development and immense resources. The scientific justification must be compelling enough to warrant the investment, which means identifying specific physics questions that demand higher energies or intensities. The Higgs boson's properties remain incompletely measured. Is it exactly the standard model Higgs, or does it have subtle differences suggesting additional physics? Why is its mass the particular value observed? Does it couple to itself as predicted, and what is the shape of the Higgs potential? These questions motivate precision Higgs studies. The matter-antimatter asymmetry question remains unresolved. Finding new sources of CP violation could finally explain the universe's composition. The nature of dark matter and dark energy demands explanation. Are there additional Higgs bosons or particles from extended sectors? Why are there 3 generations of quarks and leptons? And do they have substructure? Why are neutrinos so much lighter than other particles? And what generates their masses? Each mystery provides motivation for continued exploration. And some physicists argue that future investments should diversify beyond ever larger colliders. Precision measurements at lower energies might reveal new physics through quantum corrections rather than direct production. Neutrino experiments, searches for rare decays, measurements of fundamental symmetries, and tests of gravity at short distances all probe different aspects of nature. The field's future likely includes a portfolio of complementary approaches rather than singular focus on energy frontier machines. Regardless of specific facility choices, the scientific method remains constant. Physicists develop theories making quantitative predictions, design experiments testing those predictions, collect and analyze data, compare results to expectations, and refine understanding based on what emerges. Each measurement constrains possible theories. Each discovery raises new questions. The process spirals forward, with experimental capabilities and theoretical understanding advancing together. The cultural impact of CERN and particle physics extends beyond scientific circles. The Higgs boson discovery captured public imagination, making headlines worldwide. People who never studied physics heard about this fundamental particle and wondered about its significance. Science communicators worked to explain why finding the Higgs mattered, what it means for our understanding of reality, and why we invest resources in this research. Some explanations succeeded better than others, but the overall effect raised awareness about fundamental physics. Popular culture references CERN and the LHC frequently, sometimes accurately, and often fancifully. Movies and television shows feature particle colliders as plot devices, usually with wildly exaggerated capabilities or risks. Conspiracy theories occasionally circulate about experiments creating black holes or opening portals to other dimensions. While these ideas make for entertaining fiction, they don't reflect actual physics or real risks. CERN takes public communication seriously, providing accurate information and addressing misconceptions. The philosophical implications of particle physics discoveries provoke deep reflection. What does it mean that reality at its most fundamental level involves quantum fields and particles popping in and out of existence? How should we think about a universe where matter and energy are manifestations of underlying symmetries? Does the Standard Model's success suggest we're approaching a complete description of nature, or does it merely represent one level in an infinite hierarchy? Different thinkers answer these questions differently, drawing on physics results to inform broader worldviews. Education and outreach programs at CERN introduce thousands of students and teachers to particle physics each year. Summer schools bring graduate students for weeks of lectures from leading researchers. Teacher training programs help educators communicate modern physics to younger students. Public events and open days let citizens see detector facilities and meet scientists. These initiatives serve multiple purposes, inspiring future physicists, improving public understanding, and maintaining social support for fundamental research. Yet the economic impacts of CERN research include technological spin-offs that find applications far beyond physics. The World Wide Web was invented at CERN to help physicists share information. Medical imaging technologies derive from particle detectors. A superconducting technology developed for accelerators now aids medical equipment and other applications. Grid computing infrastructure built for data analysis serves other big data fields. These spillovers justify research investments even for those unmoved by pure curiosity about nature. Training the next generation of physicists ensures the field's continuity. Graduate students and postdoctoral researchers comprise a large fraction of collaboration members. They develop detector hardware, write analysis software, study collision data, and present results. So this hands-on experience prepares them for careers in academia, national laboratories, and industry. The problem-solving skills, computational expertise, and collaborative abilities they develop prove valuable across many sectors. The interplay between theory and experiment drives progress. Theorists propose new ideas and make predictions. Experimentalists design tests and measure outcomes. When results match predictions, confidence in theory grows. When discrepancies appear, both sides scrutinize methods and assumptions. Sometimes experiments are refined, sometimes theories are modified, and occasionally genuine new physics emerges. This dialogue between prediction and measurement has structured scientific advancement for centuries. The current anomalies that might herald new physics include potential deviations in beauty quark decays observed by LHCb. Some measurements of how beauty quarks decay into lighter particles show patterns differing from standard model predictions by several standard deviations. If confirmed, these could indicate new particles affecting the decay process. But extraordinary claims require extraordinary evidence, and the particle physics community remains cautious. Statistical fluctuations can mimic signals, and systematic uncertainties might be underestimated. More data and independent confirmations are needed. The muon's magnetic moment provides another tantalizing hint. Precision measurements at Fermilab and earlier at Brookhaven suggest the muon behaves slightly differently in magnetic fields than the standard model predicts. And this could reflect the influence of virtual particles from beyond the standard model affecting the muon's properties. However, recent theoretical calculations using different methods have shifted predictions closer to experimental values, potentially resolving the discrepancy. The situation remains under active investigation from both experimental and theoretical sides. These potential anomalies illustrate how progress happens in particle physics. Clear-cut, revolutionary discoveries like the Higgs are rare. More often, evidence accumulates gradually through many measurements. Patterns emerge from multiple experiments. Theoretical interpretations evolve as understanding deepens. The process requires patience, careful analysis, and willingness to question assumptions. It's messy and sometimes frustrating. But it's how science actually works. Looking at the broader arc of progress, the Standard Model represents a remarkable intellectual achievement. Starting from a jumble of particles discovered in cosmic rays and accelerators, physicists developed a unified theoretical framework describing how fundamental particles interact through electromagnetic, weak, and strong forces. This framework makes precise quantitative predictions that experiments have verified to extraordinary accuracy across an enormous range of energies. Few scientific theories in any field match this level of predictive success. Yet, the Standard Model is incomplete. It doesn't include gravity, leaving the universe's geometric structure outside its scope. It doesn't explain dark matter or dark energy, as it doesn't account for matter-antimatter asymmetry or neutrino masses within its original formulation. The numerical values of its parameters appear arbitrary, with particle masses and coupling strengths put in by hand rather than predicted from deeper principles. These gaps suggest the Standard Model is an effective theory, accurate within its domain, but not the final word. What lies beyond? Dozens of theoretical ideas compete for attention. Supersymmetry adds partners for all known particles. Grand unified theories merge the electromagnetic, weak, and strong forces into a single interaction at high energies. String theory reformulates physics in terms of vibrating strings rather than point particles. Loop quantum gravity quantizes space-time geometry itself. Extra dimensions modify gravity at small scales. So each approach has advocates and critics, mathematical successes and outstanding problems. Distinguishing among these ideas requires experimental input. Nature remains the ultimate arbiter. Theories must make testable predictions that experiments can verify or refute. Some predictions require energies or precision beyond current capabilities, leaving theories in a frustrating limbo where they're neither confirmed nor ruled out. This tension between theoretical ambition and experimental feasibility defines much of contemporary fundamental physics. The LHC has transformed our empirical knowledge even without finding unambiguous, beyond Standard Model particles. Measuring the Higgs boson with increasing precision constrains theoretical possibilities. Searching for supersymmetric particles and finding nothing rules out parameter space. Studying quark and lepton properties ever more carefully tests Standard Model predictions. Each measurement refines the boundary between known and unknown, illuminating where new physics must hide if it exists. As experiments push toward higher precision and energies, the questions evolve. Early accelerators discovered particles and established basic forces. Later machines refined measurements and tested electro-weak unification. The LHC confirmed the Standard Model's final missing piece and began probing for what comes next. Future facilities will continue this progression, asking ever deeper questions about nature's fundamental structure. Some mysteries might require observations beyond terrestrial experiments. Cosmic rays carry energies far exceeding any human-built accelerator. Astrophysical observations probe gravity in strong field regimes impossible to recreate on Earth. Cosmological measurements constrain conditions in the early universe. The interplay between particle physics, astrophysics, and cosmology has become essential for addressing the deepest questions. The universe itself serves as a laboratory for physics that accelerators can't reach. The human element in this scientific quest deserves recognition. Behind every measurement are people who designed detectors, wrote software, analyzed data, and interpreted results. The process involves creativity, persistence, collaboration, and occasional brilliant insight. Young researchers work exhausting hours debugging code or understanding detector responses. Senior scientists guide research directions and mentor the next generation. And technicians and engineers make everything actually function. The whole enterprise depends on diverse talents working toward shared goals. Women and underrepresented groups have historically faced barriers in physics, and active efforts continue to make the field more inclusive. Initiatives support women in physics through networking, mentoring, and addressing systemic biases. Collaborations increasingly recognize that diverse perspectives strengthen research. While substantial progress has occurred, challenges remain in achieving true equity. The cultural transformation of physics continues alongside its scientific advancement. The philosophical question of why we pursue this research admits multiple answers. Some cite practical applications and technological spin-offs. Others emphasize education and inspiring young minds. National competitiveness and international prestige matter to funding agencies, but perhaps the deepest answer involves human curiosity itself. We wonder about our place in the cosmos. We ask why things are the way they are. We push against the boundaries of knowledge because understanding brings meaning. Particle physics addresses questions humans have contemplated for millennia. What is the world made of? Why does anything exist? How did the universe begin? Ancient philosophers